So let's continue with the theory of inner product spaces. The next item is the Gram-Schmidt's process. Although the title looks very profound and stuff like that, the basic idea is very simple. In fact, it's almost geometrically self-evident, and we already used it earlier. In fact, we used it in the proof of the Cauchy-Schwarz inequality. The idea is very simple. Suppose, for example, just to keep ideas simple, let us work in R3. You're given three vectors v1, v2, v3 in R3. Assume that they are all non-zero vectors. Now, v1 may not be a unit vector. If v1 is not a unit vector, divide v1 by its length. So v1 by norm v1, let's call it w1. Now, v2 may not be perpendicular to v1. Of course, if it is perpendicular to v1 means perpendicular to w1, because w1 and v1 are proportional. So v2 is not perpendicular to v1. So what do? You resolve v2 in the tangential direction and the normal direction, right? The tangential component we denote by v2 superscript t, and the normal component we shall denote it by v2 superscript. And the t here stands for tangential and the n here stands for normal. This notation is just temporary only for this discussion, and as soon as we finish this discussion, we'll abandon this superscript t and superscript n. So the tangential component, we must write v2 as a sum of two vectors, one in the tangential direction and the other one is the normal direction. You have been doing this all the time in physics. So what is the tangential component? The magnitude. The magnitude of the tangential component is v2 dot w1, and then times the unit vector in the direction. The unit vector in the direction of v1 is w1. Once you find the tangential component, the normal component is simply v2 minus the tangential component. So we define v2 superscript n as v2 minus v2 dot w1 w1. That's all that there is to it, pretty much. Well, now this normal component may not be a unit vector. So let us make it a unit vector by dividing by the length. Okay, now you may ask, well, this normal component could be 0. That's quite possible. When will the normal component be 0? The normal component will be 0 if there's only if v2 is basically equal to, if v2 is a multiple of w1, or if v2 is a multiple of v1, in which case we can't divide. Otherwise we can divide. Let's assume that we can divide, and let's proceed further. How about v3? What are the components of v3 along w1 and w2? It is the same, v3 dot w1 w1, and the component along w2 is v3 dot w2 w2. So what is the tangent? What is the component of v3 in the plane spanned by v1 and v2? It'll be, I'm going to call it v3t. v3t is v3, the sum of these two things. The sum of these two things is a component of this vector in the plane of v1 and v2, and the normal component is the difference. And what is left over after I subtract that component in the plane in the plane spanned by v1 and v2, whatever is left over is the normal component. So v3n is v3 minus v3 dot w1 w1 minus v3 dot w2 w2. Check algebraically that, and as usual, you should do the algebraic checking. This is all geometry, but you should check it with algebraic. So this v3n is orthogonal to w1, and this v3n is orthogonal to w2. So it is indeed orthogonal to both w1 and w2. So finally, you want to make it a unit vector, divide by the length, call it w3. Of course, when will it be 0? If the normal component is 0, that means that v3 is a linear combination of w1 and w2. But if v3 is a linear combination of w1 and w2, then v3 is also a linear combination of v1 and v2. So v3 is in the plane spanned by v1 and v1. Or in other words, v3 is v1, v2, v3 is linearly dependent. If that is the case, then then this normal component will become 0, and I'm stuck. Otherwise, I can divide by the normal component. I can make that also a unit vector. And that's about it pretty much. Now let us isolate some features in this above process. Okay. First of all, if v1 is 0, the process straight away stops. I can't even continue. If v1 is not 0, I can normalize v1 and I can compute w1. And then you go to the V2. You subtract off from V2 the tangential component, you get the normal component. If the normal component is 0, the process stops. And that will happen precisely when V2 is a multiple of V1. If the normal component is not 0, the process continues. You normalize it, you get W2. Similarly, you calculate then you proceed to the next vector. Find the normal component of V3. The normal component of V3 is 0, the process stops, and that will happen if and only if V3 lies in the plane of V1, V2. Otherwise, it will continue, the process continues, and we divide V3 by the length, and we get your W3, etc. Now, we got W1, W2, W3 are mutually perpendicular unit vector. If the process goes to the last stage, then we have found W1, W2, W3 are 3 mutually perpendicular unit vectors. So let us formalize it. Orthonormal systems and orthonormal bases. A set of vectors V1, V2, Vk is in an inner product space is said to be an orthonormal system if any two of them are perpendicular and each of the vectors is a unit vector. So the system of vectors must be a system of unit vectors. And any two and they must be mutually orthogonal. Such a system is called an orthonormal system. And if this system forms a basis, we'll call it an orthonormal basis. So in R3, in our example on R3, the process went to stage K is 1, 2, or 3. We get an orthonormal system out of the given vectors, W1, W2, Wk, we got out of V1, V2, Vk. If k is 1, that means that we divided V1 by the length. And if V2, if the normal component of V2 is 0, that means that if the process stopped at that stage, then k is 1. If the process goes to the next stage, k is 2. If the process went up to the last stage, k is 3 for R3. So we got an orthonormal basis W1, W2, W3 out of the vectors V1, V2, V3. Okay, you may ask, what's the advantage? After all, for R3, we do have a very nice orthonormal basis, E1 cap, E2 cap, E3 cap. So why all this excitement about doing this whole thing and obtaining a W1, W2, W3? The feature about this W1, W2, W3 is the following. Remember that W1 is a multiple of V1 and V1 is a multiple of W1. So linear span of V1 is the same as the linear span of W1. And then you got W1 and W2 out of V1 and V2. So and what was W2? W2 was V2n, the normal component of V2 divided by the length. But what was the normal component of V2? V2 minus some multiple of V1, right? V2 minus some multiple of W1. That was so therefore W2 can be obtained as a linear combination of V1 and V2. So likewise, V2 can be obtained as a linear combination of W1 and W2. So linear span of V1, V2 is the same as the linear span of W1, W2. And you can check that the linear span of V1, V2, V3 is the same as the linear span of W1, W2, W3. This is the new feature of the basis W1, W2, W3. Let us formalize this process in any number of dimensions. So we talk about in any inner product space, not necessarily only the dot product. We can do it in any inner product space V. So you start out with a bunch of vectors V1, V2, Vk, be a set of non-zero vectors in an inner product space V. We construct a sequence of vectors as follows. The first vector we construct is W1, which is simply V1 by length of V1. Okay. I can divide because my vectors are non-zero. Then we construct the normal component. So you subtract from V2 the component in the direction of W1, and what you are left with the normal component V2 minus V2 dot W1 W1. If this V2n is 0, then stop. Else divide by its length and get a unit vector. Then go to the next one. V3n. From V3, subtract the component in the plane of V1 and V2. But we saw that the plane of V1 and V2 is the same as the plane of W1 and W2. So we subtract the tangential component, and what is left over is V3n, the normal component, V3 minus V3 dot W2 W2 minus V3 dot W1 W1. If this V3n is 0, stop. And we conclude if V3 is 0 stop, and the conclusion is that V3 is a linear combination of W1 and W2, or V3 is a linear combination of V1 and V2. Else, divide by the length and go to the next stage. So assume that the process stops at the I plus first stage, that is V I plus 1 n is 0. Then what we have is that the first, but it did not stop at the previous stage, so we got up to I, we could W1, W2, Wi is an orthonormal system. And such that such that linear span of V1, V2, Vj is the same as the linear span of W1, W2, Wj for j equal to 1, 2 up to I. And the process continues to the next kth stage. That is, if I'm able to go right up to the kth stage, where k is the total number of vectors that you got right at the beginning, then the vectors are linearly, then the original vectors are linearly independent. And the process terminates strictly before the kth stage. That is, if Vln is 0 for some L strictly less than k, then the original vectors are linearly dependent. This gives you yet another way to test whether a bunch of vectors are linearly dependent or linearly independent. Clearly, you can write a computer program to carry this out. You can certainly write a computer program to carry this out, and the computer coughs out, suppose you got 10 vectors, and the computer coughs out W1, W2, W8, and then at the next stage, the V9 superscript n became 0. Then the computer will tell you that the process has stopped. After the 8th stage, it is not able to normalize the 9th vector because it is 0. Then you know two things. The original set of vectors V1, V2, V10 or V1, V2, Vk were linearly dependent. Not only that, you know that the first 8 vectors, suppose your L is 9, suppose V9 superscript n is 0, that means that the first 8 vectors were linearly independent. And the 9th vector is a linear combination of the previous 8. So this is a slightly more superior thing because it is telling you that which vectors is a linear combination of which others. So this gives you a very convenient, another way to test linear dependence or linear independence. Okay, so this is the theorem. Well, the theorem appears pretty long, but it is routine. The statements are pretty routine. And the proof is also very routine. The proof is practically self-evident. Now, check by taking inner product, dot product, that W1 and W2 are perpendicular. It's absolutely clear that W1 and W2 are perpendicular, right? Because if I take V2n and dot it with W1, what are you going to get? W1 dot W1 is 1 because W1 is a unit vector. We get V2 dot W1 minus V2 dot W1, that is 0. So this vector W1 is orthogonal to the next vector V2n, and V2n has been divided by its length and we got W2. So W1 and W2 are orthogonal. Similarly, check W1 and W3 are orthogonal. How do you get W3? You get W3 from V3n by dividing by the length. So take the dot product W1 V3 dot W1 and W1 dot W1 is 1. So V3 dot W1 and V3 dot W1, that becomes 0. And the middle term, what about the middle term? W1 dot W2 is already 0, remember? W1 dot W2 is already 0. So again, we check that this W1 is orthogonal to W3. So first we check W1 and W2 are orthogonal. We can check that W2 and W3 are orthogonal, and W1 and W3 are orthogonal. That can keep checking. So the orthogonality is pretty easy. 3 follows from 2. 3 follows from 2. Now, what does 2 say? 2 says that linear span of V1, V2, Vj is the same as the linear span of W1, W2, Wj. Now, if the process goes all the way up to k, that means linear span of V1, V2, Vk will be the same as linear span of W1, W2, Wk. And this linear span, so W1, W2, Wk, the linear span of W1, W2, Wk. I have taken this vector space, linear span of W1, W2, Wk. So W1, W2, Wk is a generating set. And they're orthogonal, they're orthonormal, they're orthogonal unit vectors. So they're linearly independent. So this is a k-dimensional space. In a k-dimensional space, a generating set with k elements will be linearly independent. So I'm assuming that the process goes up to kth stage, right? That we are in item number 3. We want to show that 3 follows from 2. We're going to assume 2. We're assuming 2. And so the j is k. And from the right hand side, it's clear that the dimension of the space is k. And from the left hand side, linear span of v1, v2, vk. So we got a generating set consisting of k vectors in a k dimensional space. And so this generating set is automatically linearly independent. Okay, so that's what I mean. I say 3 follows from 2. So here is the argument which I just spelled out. All right. And if, as I said, if at the nth stage VLN happens to be 0, that means exactly VL will be VL dot W1 W1 VL dot WL minus 1 WL minus 1, which means VL is a linear combination of the previous ones. VL is a linear combination of W1 W2 WL L minus 1, but linear span of W1 W2 WL minus 1 is the same as a linear span of V1 V2 VL minus 1. Okay, so VL happens to be a linear span of the previous ones. So the complete set is linearly dependent. So now we have to prove 2. What is 2? 2 is this fact that linear span of V1 is the same as linear span of W1. Linear span of V1 V2 is the same as linear span of W1 W2, etc., etc., etc. Okay, so for K, so now let us prove this by induction. Linear span of W1 equal to linear span of V1. That is absolutely clear because W1 is simply obtained from V1 by dividing by the length of V1. So you can obtain W1 from V1 and you can obtain V1 from W1. No issues about that. Assume inductively that linear span of W1, W2, WL minus 1 is the same as linear span of V1, V2, VL minus 1. Correct? Now, let us assume that the process has gone to the next stage. That means that VLN was a non-zero vector and I divided it by the length and I got WL. And so now WL is now, so what is WL? So what is VL? What is the definition of VL, by the way? VLN is from VL you subtract off what? What will you subtract from VL? The components in the direction of W1, W2, WL minus. So you look at VL minus VL dot W1, W1 minus VL dot W2, W2, etc. So this VLN is obviously in the linear span of VL, W1, W2, WL minus 1. That means, and WL is obtained by dividing by the length. So WL is in the linear span of VL and then W1, W2, WL minus 1. But in other words, WL can be obtained as a linear combination of these vectors. But W1, W2, WL minus 1 themselves can be obtained as a linear combination of V1, V2, VL minus 1. Therefore, WL can be obtained as a linear combination of V1, V2, VL minus 1 and VL. We have used induction hypothesis to go from this step to this step, by the way. And now by induction hypothesis, W1, W2, WL minus 1 are the linear span of these. And now we have shown that WL is also in the linear span of these. So all the W's are the linear span of the V's. So the linear span of the W's is sitting inside the linear span of the V's. And to get the reverse inclusion, it is exactly similar. Now we started out with looking at VLN. Now we look at VL. VL is again VLN plus because VLN is VL minus So what the right hand side belongs to the linear span of the first vector VLN and then W1, W2, WL minus 1. But again, by induction, but this linear span of, but this WLN is basically a multiple of, VLN is a multiple of WL. So this linear span is going to be the same as the linear span of W1, W2, WL minus 1, WL. Because the last vector is simply obtained from the first one by dividing by the length. Now use induction hypothesis. And again you will conclude that the V's all lie in the linear span of, because V1, V2, VL minus 1 are obtainable from W1, W2, WL minus 1 already. And we are now saying that VL is also obtained by the linear combination of these. But the first L minus 1 are already linear combinations. So that's what it says, that all the vectors V1, V2, VL all are obtainable from all the V's are obtainable from all the W's. That's what the argument says. So the proof is complete. In both directions, we get the inclusion. All right. So we can also, in fact, this reverse inclusion is really not required. Question: once you get this inclusion, can you say that this inclusion must be an equality? You can, because because both sides are L-dimensional vector spaces. So if you have two L-dimensional vector spaces and one of them is lying inside the other, then it must be equal. If you have two subspaces, say subspaces, let us say S1 and S2. S1 and S2 are two vector subspaces, and S1 is sitting inside S2. But the dimension of S1 and dimension of S2 are equal. They're both equal to L in this case. And so S1 must be equal to S2. Can you please think about this? And because if you do that, then we can short circuit the proof and we can stop here. And this argument is not required. But this argument is very elementary and easy. So there is no harm in giving a complete argument independently. So now, given a vector space V endowed with an inner product, I can find an orthonormal basis. In fact, take any basis B consisting of vectors V1, V2, Vk. We can find an orthonormal basis W1, W2, Wk such that the linear span of V1, V2, Vl is the same as the linear span of W1, W2, Wl for L equal to 1, 2, 3 up to L, up to K. This is called the Gram-Schmidt's. This is called the Gram-Schmidt's method, Gram-Schmidt's process. Now, let us apply the Gram-Schmidt's process to a practical example. So you take three vectors, 1, 1, 1 column, 1, 1, 0 column, 1, 0, 0. The first vector is not a unit vector, divided by the length. What is the length of this vector? 1 up root 3, so we must divide by 1 upon root 3. We must divide by root 3, excuse me. So W1 is 1 upon root 3, column 1, 1, 1. Now how do I get, now how to proceed? What is the next vector V2? 1, 1, 0 column. From this V2, you must subtract of what? You must subtract of the component in the direction of W1, right? So you must subtract of the component. So V1, W1 dot V2, W1. This you must subtract this off. So 1, 1, 0 transpose, that's V2 itself. And now I have to calculate the dot product of W1 and V2. V2 is here, 1, 1, 0 transpose. And 1, 1, 1 transpose is W1 with the 1 upon root 3 factor thrown in. So when you do that, you're going to get 2 upon root 3. The dot product of these two is going to be 2 upon root 3. 2 upon root 3. And then times W1. W1 is what? 1, 1, 1 transpose. There should be a transpose here. It should be 1, 1, 1 transpose into 1 upon root 3. So 1 upon root 3, 2 upon root 3 is 2 by 3. 2 by 3 times 1, 1, 1 transpose. It's a very, very trivial typographical error. So you can download this one. When I give you the PDF files, you can make the change yourself. So 1 minus 2/3, 1/3. 1 minus 2/3, again 1/3. And 0 minus 2/3 is minus 2/3. The second vector is 1/3, 1/3 minus 2/3. Or you can say 1/3 times 1, 1 minus 2. Is it a unit vector? No, it's not a unit vector. And so you have to divide by the length. When you do that, you're going to get 1, 1 minus 2. Transpose should be there again. There should be a transpose here, and there should be a transpose here, and there should be a transpose here. W2 is 1, 1 minus 2 transpose divided by root 6. Then V3. What about V3 transpose? V3 transpose is from V3 minus V3 dot W1 W1 minus V3 dot W2 W2. You have with you V3 110 column. You have with you W1. You have with you W2. You just have to calculate the dot product and you have to do the algebra. You're going to get 1/2, and then you're going to get 1/2 of 1 minus 1 0. And so you have to divide by the you have to make it a unit vector. So you're going to get 1 minus 1 0 transpose upon root 2. That's how the Gram-Schmidt's process goes. Okay. Now, so here is an exercise for you. Suppose A is a 3 cross 3 matrix whose rows are orthonormal. Prove that the columns of A are also orthonormal. Let's see how to do that. A is a 3 cross 3 matrix whose rows are orthonormal. A is R1, R2, R3. R1 and R2, R3 are orthonormal system. Look at A transpose and look at A transpose. What is the first column of A transpose? R1 transpose. Let's call R1 transpose as C1, R2 transpose as C2, and R3 transpose as C3. What is the ijth entry of the product AA transpose? What is the ijth entry? It is Ri Cj. But what is Cj? Cj is Rj transpose. So it is Ri Rj transpose. It is a dot product Ri and Rj. But Ri, R1, R2, R3 are orthonormal. So the dot product of Ri and Rj will be 0 if I is not equal to j, and 1 if I is equal to j. In other words, AA transpose is a identity matrix, is the 3 by 3 identity matrix. In other words, A is an invertible matrix. Remember that if you have a square matrix A such that AB equal to I, then compulsorily BA is also equal to I, no? Remember, we have done that. So because AA transpose is I, we can now say that A transpose A is I. Now we say that A transpose A is I. Now if you look at A transpose A is I, that means that the column, from that you can infer that the columns of A are, the rows of A transpose are also orthonormal. So the columns of A are orthonormal. Please write this out for the 3 by 3 case explicitly and work it out. Please. Yeah. And once you work out the 3 by 3 case, it should be abundantly clear to you that there's nothing sacred about the number 3. The same song and dance will simply go through for the n cross n matrices. If A is an n cross n matrix whose rows are orthonormal, then the columns will also be orthonormal. There is no change in the argument. The next exercise. Let U and V be orthogonal unit vectors. Two vectors which are mutually perpendicular. And they are unit vectors. Prove that U cos theta plus V sin theta is a circle. Now, what exactly is the dot product U dot U? U dot U or norm U squared is the distance of the point. Suppose U is x1, x2, x3, xn. Then the distance of the point x1, x2, xn from the origin, the square of this distance. What is that? But the distance formula, x1 squared plus x2 squared plus dot 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 plus xn squared. That is U dot U. So now let us take this vector U cos theta plus V sin theta, inner product with U cos theta plus V sin theta. Dot product of U cos theta plus V sin theta with itself. You're going to get U dot U cos squared theta. You're going to get V dot V sin squared theta. And then you're going to get U dot V cos theta sin theta, V dot U sin theta cos theta. But U dot V and V dot U are 0. The two vectors are orthogonal. And U dot U is 1 and V dot V is 1. So, and cos squared theta plus sin squared theta is 1. So as theta varies from 0 to 2 pi, this point U cos theta plus V sin theta traces out a circle. How do I know it's a circle? Because a plane, because these points lie on the plane spanned by U and V. What is a circle? A circle is a locus of points, is a locus of point moving in a plane such that the distance from the origin is fixed. So that's exactly what it is. What is the plane? It is a linear span of u and v. And what is the distance from the origin? 1. We just checked. Now you consider two vectors, 1 upon root 6, 1 minus 1, 2, and the other vector is minus 2, 0, 1. And then normalized with a 1 upon root 5. These two vectors are orthonormal, right? Because they are unit vectors and they are perpendicular. So I got two vectors, call them V and W. I want you to complete, so if I put them together, I'll get a 3 by 2 matrix. But I want a 3 by 3 matrix. I need one more column Z, such that the matrix that I get by putting the columns together, V, W, Z, is a matrix such that A transpose A equal to identity. I want to complete this V, W and add a third vector Z. And there is augment a third column Z such that the 3 by 3 matrix has the property that A transpose A is the identity matrix. You get your answer will be quick, and you'll tell me the answer in lightning speed. You will say that you will take the cross product. Sure, that's correct. But what if I give you n minus 1 vectors, which are mutually perpendicular unit vectors, and I ask you for one more vector un, such that the matrix that I get by stringing these columns together has the property that A transpose A is identity. Then you can't use cross products. So try to give an argument which will work in general dimensions Rn. I think we'll stop this capsule here and we'll continue this next capsule.